Finding alien planets is like spotting a firefly next to a supernova. That's the challenge of finding exoplanets. Yet we've found thousands. Imagine trying to spot a firefly next to a spotlight from hundreds of miles away. That's essentially the astronomical hurdle we overcome daily in our quest to find worlds orbiting stars beyond our sun. These distant worlds are incredibly faint compared to the blazing brilliance of their host stars, often a billion times dimmer in visible light, making direct observation nearly impossible with current technology for most cases. It's like trying to find a tiny, dark pebble orbiting a blinding lighthouse. This extreme contrast and small angular separation mean that instead of directly seeing these alien worlds, we've had to become cosmic detectives, inferring their presence through the subtle clues they leave behind. The story of exoplanet discovery is a testament to human ingenuity, pushing the boundaries of what we thought was possible. And it all began with a scientific revolution that reshaped our understanding of the universe. For millennia, humanity believed Earth was the center of everything, and our sun was just another star among many, with its own unique retinue of planets. The idea of planets orbiting other stars was pure science fiction, a philosophical curiosity rather than a scientific pursuit. Even as recently as the late 20th century, the existence of exoplanets remained unconfirmed. But then, in 1995, a breakthrough occurred. Swiss astronomers Michel Mayor and Didier Queloz announced the discovery of 51 Pegasi b, a gas giant orbiting its star in a mere 4 days. This wasn't just any planet. It was a hot Jupiter, a massive world orbiting incredibly close to its star, a configuration entirely unlike anything in our own solar system. This discovery shattered preconceived notions about planetary system formation and ignited a furious race to find more. The universe, it turned out, was far stranger and more diverse than we had ever dared to imagine, and we were just beginning to scratch the surface of its secrets. So, how do you find something you can't see? The answer lies in the subtle ways a planet influences its host star. One of the most successful techniques is the radial velocity method, also known as the Doppler wobble method. Think of a star and its planet as two dancers locked in an embrace. While the planet orbits the star also subtly orbits the common center of mass, like a tiny wobble. This wobble causes the star to move slightly towards and away from us. When the star moves towards us, its light waves are compressed, shifting towards the blue end of the spectrum, a blue shift. When it moves away, the light waves are stretched, shifting towards the red end, a red shift. By meticulously measuring these tiny Doppler shifts in the star's light, astronomers can detect the gravitational tug of an unseen planet. The larger the planet and the closer it is to its star, the more pronounced the wobble and the easier it is to detect. This method has been instrumental in finding many of the first exoplanets, particularly massive gas giants, and it continues to provide crucial data about their masses and orbital periods. But what if the planet isn't massive enough to create a detectable wobble, or if its orbit isn't aligned just right? That's where the transit method comes in, a technique that has revolutionized exoplanet discovery and given us a census of thousands of alien worlds. Imagine a tiny ant crawling across the face of a distant light bulb. For a brief period, the ant will block a minuscule amount of the light, causing the bulb to dim ever so slightly. That's precisely what happens when an exoplanet passes directly in front of its host star from our perspective. This event, called a transit, causes a temporary, periodic dip in the star's brightness. By carefully monitoring the light from millions of stars, telescopes like NASA's Kepler Space Telescope and the Transiting Exoplanet Survey Satellite, or TESS, have identified thousands of these subtle dimming events. The amount of dimming tells us the size of the planet relative to its star, and the regularity of the dips reveals its orbital period. The transit method is particularly powerful because it allows us to determine not only the planet's size, but also, when combined with radial velocity data, its density, offering clues about its composition. This method has revealed an astonishing diversity of planetary sizes, from rocky super-Earths to mini-Neptunes, far beyond the familiar categories of our own solar system. But what if the planet never crosses in front of its star from our vantage point? Sometimes, the universe offers us a cosmic magnifying glass. This is the principle behind gravitational microlensing, a phenomenon predicted by Einstein's theory of general relativity. When a foreground star, acting as a lens, passes almost perfectly in front of a more distant background star, the foreground star's gravity bends and magnifies the light from the background star. If the foreground star also has a planet, that planet's gravity can create an additional, brief flicker in the magnified light. This fleeting signal is incredibly difficult to catch, as it only happens once and requires precise alignment. However, it's particularly good at finding planets that are far from their stars, or even rogue planets that aren't orbiting any star at all. While less common than transits or radial velocity, microlensing offers a unique window into populations of planets that other methods might miss. These indirect detection methods have painted a vibrant picture of a universe teeming with planets, but the ultimate goal remains direct imaging, actually seeing these distant worlds. Direct imaging is the holy grail of exoplanet research, and it's where the firefly next to a spotlight analogy becomes most starkly apparent. Because exoplanets are so incredibly faint and so close to their blinding host stars, directly capturing their light is an immense technical challenge. It requires instruments that can block out the star's light, like a tiny, perfectly placed eclipse, and then gather the faint light from the planet itself. Techniques like coronagraphy, which uses a mask to block the star's light, and adaptive optics, which corrects for the blurring effects of Earth's atmosphere, are making this possible for a select few, usually very large and very young planets orbiting relatively nearby stars. The James Webb Space Telescope, with its incredible infrared sensitivity and coronagraphic capabilities, is pushing the boundaries of what we can directly image, allowing us to study the atmospheres of these distant worlds and search for potential biosignatures, chemical signs of life. Imagine being able to analyze the atmospheric composition of an alien world, searching for the telltale signs of oxygen, methane, or other molecules that could indicate biological activity. The implications are staggering, but the technical hurdles remain immense. The sheer diversity of exoplanets we've discovered is truly mind-boggling. We've found hot Jupiters orbiting their stars closer than Mercury orbits our Sun, super-Earths that are larger than Earth but smaller than Neptune, and even mini-Neptunes with no equivalent in our own solar system. Some planets are thought to be ocean worlds, entirely covered in water, while others are lava worlds, with surfaces molten from extreme heat. We've even found planets orbiting two stars, like the fictional Tatooine from Star Wars. Each new discovery challenges our understanding of planetary formation and evolution, forcing us to rethink what's possible in the universe. The more we look, the more we realize that our solar system, once thought to be the standard, is just one of countless configurations. The universe is far more imaginative than we ever gave it credit for, and the possibilities for life, in all its myriad forms, seem to expand with every new world we find. The study of exoplanets is more than just cataloging distant worlds. It's a profound journey of self-discovery. Each new planet we find helps us understand our place in the cosmos a little better. It refines our models of how planets form, how they evolve, and what conditions might be necessary for life to emerge. The search for exoplanets is, in essence, a search for answers to some of humanity's oldest questions. Are we alone? Is there life beyond Earth? And if so, what forms might it take? The next generation of telescopes, both space-based and ground-based, will push the boundaries even further, allowing us to characterize the atmospheres of smaller, potentially habitable worlds with unprecedented detail. We are on the cusp of a new era of discovery, one that promises to reveal even more astonishing secrets about the universe and our place within it. What incredible alien worlds await our discovery, and what will they teach us about ourselves?